OCR A, A-level physics. This is my 5th video on gravity and astrophysics. And I'm going to look at some equations that you need to know. Okay, so star equations for want of a better title. Okay, now the spectrum of light emitted by a star. We talked a lot about this in the last video. I'm not bothered about the absorption lines now, just the actual hump, this shape, okay? It's called black body radiation. And the shape shows the intensity of different wavelengths, okay? And the spectrum very much depends on the temperature, the surface temperature of the star. Two important things: the hotter the star is, the more radiation it emits. So look at the numbers, look at the temperatures, yeah? The hotter the star is, the more radiation it emits, obviously. And then secondly, the hotter the star is, then the peak of the curve happens at a smaller wavelength. So if you look, as the temperature gets bigger, look where the peak is on all of these curves, and you'll see that the peak happens at a smaller wavelength when the temperature is bigger. And so we get to Wein's displacement law, or is it Wein's displacement law? I don't know. But it's basically that the peak, lambda max, that's where the peak occurs, as I was just talking about, is inversely proportional to the temperature. So the higher the temperature, then the peak happens at a smaller wavelength. And the constant is Wein's displacement constant, and you'll be given a value for that. So if you can get the value for this peak off a graph, or if you're given it, you can work out the surface temperature of the star. So there's a little sum for you to do. So pause the video and do it. And the surface temperature of the sun is, there you go, about 5,300 Kelvin. Now, the luminosity of a star. The luminosity is how much energy it emits every second. And it's capital L, and it's measured in watts, which is joules per second. Okay? Now, the luminosity will depend on the surface temperature of the star. The hotter it is, the more radiation it will emit, and it will also depend on its surface area. The equation is Stefan's law. Now, looking at this equation, so L is 4 pi r squared sigma times t to the 4. This 4 pi r squared, you might recognize that. That's the surface area of a sphere, isn't it? Sigma is a constant, and T is the temperature, T to the 4. You'll be given the value of the constant, the Stefan constant. And having said all of that, there's a little sum for you to do. So, and it says in the specification, using this to calculate radius. So this is probably what you're going to have to do. So have a go at this. And the answer is, there you go, 5.5 times 10 to the 10 meters. Very often the luminosity is given as kind of compared to our sun, by the way. What is a light year? A light year is the distance that light travels in space in a year. So 3 times 10 to the 8 meters per second, and then how many seconds are there in a year? Multiply them together, and it's a big number. It's about 9.5 times 10 to the 15 meters. It's a big distance. The next, apart from our sun, the closest star to us, Proxima Centauri. Okay, it's in Centaur. Proxima means very close. It's proximate to us. About 4.5 light years, 4.25 light years away. That's the nearest star. The Milky Way, the diameter of the Milky Way is about 100,000 light years. The next nearest galaxy is Andromeda. That's about 2.5 million light years away. One of the furthest galaxies we have observed is this thing here. That's 13.6 billion light years, 13.6 gigalight years away. An interesting little fact for you, Betelgeuse or Betelgeuse may have gone supernova about 600 years ago, and we may see it happen very soon because it's about 646 light years away. Betelgeuse, a red giant in Orion. Heliocentric parallax, what's that then? Well, look at the diagram. You've got the Earth going around the Sun, and then if you were looking at a nearby star, now in the background you've got very, very, very distant stars. As the Earth goes round the Sun, you're looking at this star from different angles. If you look at this animation that I've made here, okay, so in a year, then the star appears to move, and that's because you are looking at it from a different angle. As the Earth orbits the Sun, nearby stars appear to move against the background of much more distant stars, and this effect is called heliocentric because the Sun is in the middle. Heliocentric parallax. And if you measure the parallax angle, you can work out how far away the star is. Yes? So the closer the star is to us, the bigger the parallax angle. We are talking very, very small angles here, by the way. This diagram is obviously not to scale. Now, what is a parsec? A parsec is a unit of distance. It's about 3.26 light years is a parsec. Definition of a parsec: if a star was 1 parsec away, then its parallax angle would be 1 second, 1 arc second. You know that there's 360 degrees in a circle, and then in 1 degree you've got 60 minutes, and then in 1 minute you've got 60 arc seconds. So it's a tiny, tiny angle. And then the distance of a star in parsecs is therefore given by d is 1 over p. So d is in parsecs and p is the parallax angle in radians. Have a go at that. Rigel has a parallax angle of thingy. How far away is it? And the answer is 265 parsecs, which is about 860 light years. So these are the 3 equations that we've looked at. Just a little summary. To calculate the surface temperature of a star, you've got this Wein's displacement law. To calculate the radius, it's probably what you have to do, you use this equation here, Stefan's law. And then to calculate the distance in parsecs, using the parallax angle, you've got this equation here.